innovating, connecting, and collaborating with the academia. Engineering, telecommunications, and internet through our partnerships with the academia. So, Lucas, can you give us the remote control back? Thank you. Okay. Thank you. Thank you for staying to listen to my talk. I'm going to present my experience, our experience at the University of Montevideo, the University of the Republic, showing how we generated synergies with other institutions such as an ISP, the National Telephone Company in Uruguay, and in this case with LACNIC. So our work is oriented to BGP protocol and how to improve the use, to understand it better, and how it can help us understand to better design a network. Clearly, this is like the base of a hyperconnected world that we are living, experiencing today. And we can innovate in these areas, and this is crucial precisely not just for the academia, but also for the technological and the economic, social, and technological development of society. This is a partnership experience, including the academia and the rest of society. So, well, actually, at the university, we work in cooperating with the companies, not just with the internet, clearly, and there are different examples of technological innovation, of joint work, trying to develop solutions to solve challenges that are not so trivial, that are not so ready-made, that or plug and play, where you buy the product and with that you solve things. And we have even more than once we have nominated for research, trying to get funds, either with the government contest or the FRIDA fund too. And we have also participated in hackathons with where the industry and the academia.
So very often startups arise from these experiences. And finally, and not least important, we have the issue of mentoring, helping others to grow and to establish and apply their experience and innovation in the field of technologies. So let us now go to the topic of this presentation. Let's speak about BGP. This began some time ago, back in 2017, 2018. We started to work in improving the iBGP topology design of an ISP. With that aim, we needed to better understand how BGP worked, how information is propagated in the ISP, how it reaches all the routers, as well as the potential problems that this could produce. And then the security issues in terms of availability, integrity, etc. So the first part of this work began, as I was saying, with trying to better understand how within an autonomous system things could be organized. What we were interested in at the time was how to select the route reflectors and how to establish the BGP sessions between the different nodes in this network. The aim was to preserve the information, allowing it to reach all the routers, but also to be more efficient in terms of the performance. So this is a new paradigm, relatively new paradigm. Initially, we had a mesh where all the nodes were interconnected, but this generates a lot of traffic, and sometimes managing this becomes quite difficult. So the use of route reflectors at the time offered an alternative, but also posed challenges, because very often, due to misconfigurations, problems would arise. For example, in the sense of not all the information reaching all the routers. So the important thing here was to base ourselves on the decision-making algorithm as to which route to select. This is established in the relevant RFC on BGP, and also basing ourselves on what would be the underlying IGP network that the relevant autonomous system has. So this ends up being an overlay problem. So several layers are connected and they are interrelated in terms of how they function. To solve this problem, at the time, we applied several mathematical models to research the operations. We considered different scenarios. For example, pure IP, and then on MPLS as well. All this bearing in mind the topic of resilience. So what would occur if a node crashes, or because this is the problem when we have only a limited number of routers which receive the information, which are the route reflectors. Is if you just have one, that's fine because there is less traffic, but if that one crashes, that does become a problem. The same with the links. So this information was an ISP. This was the source of information. This was the internal network. So based on that, and beyond the mathematical models that we developed and that we discussed collaboratively with this provider to see how we would implement this or whether it was convenience according to the reality, we also obtained secondary results at the time. We later saw that these became relevant. On one hand, we defined what we called the prefix trees. This is how the entire spectrum of the IP addresses is built. These are the prefixes that are disseminated along the internet. And also the height of that tree. Ultimately, it was important to have this information because this implies how the information will be distributed. And at the same time, we introduced the concept of prefix class. These were previously based on the ASBRs. What does this mean? This means that if we have a prefix that comes, as you see in the example, if it comes from the border router 1 or border router 2, and another one comes from border router 2 or 3, these were two different classes, but all the prefixes that meet these conditions can be grouped. As a result, we went at that time, I'm speaking of the year 2020, at that time we went from over 9 million eBGP updates, which we received at the time. And with the BGP decision process, this then became 800,000 prefixes, and then we discarded the prefixes with very low specificity. We then had some 150,000 prefixes, but this was still a lot for the purpose of modeling. But then, at that time, we had 7 ASBRs, then we had 10. The network started to grow. So we applied the concept of grouping this into prefix classes, and then we had 7 prefix classes. Of course, a much smaller number than the 800,000 original prefixes. So with this, we could explain what was happening with the internet. This then significantly reduces the type of problem that we wished to tackle. The other problem is that there is like a high concentration of the largest share of the six most extensive prefixes. So we continued to work. This was the following year. We had a new topology. The network increased. And although the network was duplicated, and as we saw in this previous slide, where we had the tree, we have 2 to the n minus 1 classes. So it could potentially increase potentially. If I go from 10 to 20 classes, potentially I could have 1 million. From 10 to 20 ASBRs, I could have 1 million because it's 2 to the 20th minus 1. But in fact, it was a couple of hundred. So this ratifies our theory that although these might seem quite a lot, they are still much less than the hundreds of thousands or 1 million classes that we had originally. So we continued to advance. A new concept was introduced. We had been working on this with a master's degree student who's about to graduate now. And we said, well, how can we continue characterizing this network even if we don't have the internal information? Because not always the ISPs come and say, well, come and this is my topology. So we then said, well, now we can look at other type of information. In this case, where do these prefixes come from? This is something that we can see because one of the major attributes we have in BGP is the AS path. So we see through all the ASs through which this goes through. And this is very important because this is useful to prevent loops, but also helps us to see which the route is and specifically to see what the origin is. So this is a classification of the classes, the information that comes here with the updates, with the BGP updates. We can then obtain the classes in different ways. Now the interesting thing here is that for the same networks for which we had seen the previous concept, the algorithms were now run to try to reduce the number of classes. And we obtained similar numbers, and we're measuring this in a different way. So we ran different tests, the amount was similar, and we saw that a few classes concentrate a large percentage of prefixes that circulate. So we published a couple of things, also a paper that was presented in one of the previous LACNICs in Colombia. So after that, we said, well, we now have to model an ISP to see whether a typical ISP so we could study the amount of classes. We started to see which would be the information sources. It is easy when this comes from the ISP itself. But to tell the truth, there are quite a lot of repository around in the internet that contain very useful information. On routing, we have RIPE RIS, route views. We also have some theories in CAIDA, concepts as to how these autonomous systems are connected with one another, the relationships between the ASs. We also had to run some models and estimations. For example, how many ASBRs could this autonomous system have? Also, where do the connectors of that autonomous system connect? Because that autonomous system is connected to one or more potential providers or peers. So what is the type of link they have and how do they get connected? How are they connected with an IXPs? These are all very relevant players in the current internet reality. And then how do they reconnect with all the other peers? Then finally, once all this model was set up, all this theoretical model had been set up, and with certain assumptions, basically all based on publicly available information. And in case we didn't have the information, we prepared networks in order to estimate the classes. What we did then was to verify with Jose, a master's degree student. We verified the theoretical model against the ISP from which we had the information. We saw that the network had increased, the ISPs increased double the amount, and we also increased the estimations based on the public available ISP information in these repositories. We saw then the number of estimated classes for each. So we see that the numbers are quite similar with a very low error margin, and only a limited number of classes concentrate the largest number of prefixes. This is a behavior that we had already noted. And as I was saying, all this was done randomly and also trying to estimate this parameter. And then the standard deviation is around 27%. To conclude, and in terms of future work, this is a demonstration of an interinstitutional work. We have worked with different institutions in the industry. We work together with the academia and also LACNIC. We have to thank LACNIC, who provided information and also helped us financially in order to collaborate with this project. On the other hand, we introduced this concept of classes, and the importance is to try and simplify that super complex reality, namely which are all the BGP updates that we have in the network, in order to better model our networks and better understand how this information circulates in the autonomous system. So the idea is to continue working along this line and also to include some security aspects and how this affects this. This is a hot topic. Security is a hot topic today. So according to the available techniques and how this is being developed.
Any questions? Thank you. There you have my email, just in case you want to contact me.